All right, good afternoon. So a couple of things. I just want to take today to wrap up chapter 6, I guess it is, and talk about a little bit more about bagging and the random forest. And then just mention boosting what it is, and then just kind of tell you not to do it unless you feel comfortable. So start with these ones that we're working through, and then once you feel comfortable, then you can start working with boosting. But we'll talk more about that. So we've got our test on Thursday, right? Test 2. Oh, no, you guys are going to do great. You guys are sitting pretty after test 1. Everyone did so well, right? I'm going to make it a little bit harder, right? You've seen some of those assignment questions. Again, the assignments, I'm pretty much just going to make sure that you are good with all those assignment questions. So I'm going to smush them all together and make it the test. But there are some harder questions on there, right? So really make sure that you know how to manipulate those calculations. Wait, hey, what happened? Jumped in. Test number 2. On Thursday, right? It'll be open all day. And by all day, I mean kind of midnight to midnight on Thursday. So that way, if you're in a different time zone or whatever, then you can kind of work with that, right? And so it'll be open for pretty well 24 hours, and it'll be a timed test. So it's going to be an hour and 20-minute timed, because that's how long our lecture is, right? So I may as well make it that length, right? I think you won't need the full hour and 20 minutes, but just in case you hit a snag, right? Can't remember how many questions I decided on, but an hour and 20 minutes worth. How about that? So on Thursday, and open all day, 1 hour and 20 minutes, timed quiz. Can't remember. I think 2 or 3 kind of hand calculation questions. Right, so make sure you practice all those ones that were on the assignments. Some of those logistic regression ones are a little bit tricky, right? Until you get the hang of it. So I'm definitely going to make you do those, right? So just be prepared for that. Okay. And I want you to submit any written work. So it doesn't have to be, but if you need me to go back and refer to your written work, right, it has to be in there. And I can't remember, I think I made you do that for test 1. Oh no, because it was all multiple choice, right? But now we're doing computation. So because we're doing potentially written work, right? So submit any written work. It's not for marks, right? But submit any written work to the Dropbox on Moodle within 10 minutes of completing the test. Okay, so from the time that you submit the test, you'll have 10 minutes to upload that work. Okay, so make sure that it's all ready to go, because 10 minutes just kind of flies by. Otherwise, I can't look at it. Okay, I can, I won't. So submit any written work to the Dropbox on Moodle within 10 minutes of submitting your test. In case you need me to look at it. Oh yeah, so if you want to, you can use R. right? So however you want to show your work, that's fine, right? If you want to upload a PDF of your R, right? If you want to write it in Markdown or something like that and just show your R, that's totally fine. However you choose to show your work, right? So as you kind of review these assignments that we've had from chapters 4, 5, and 6, right? Then make sure that you're comfortable with however you're going to summarize that work. Okay, it's not for marks, but it's a safety net, right? If you need me to, oh, I didn't enter that number correctly, but I did it in my work, right? That type of situation, then you can send me an email or you can text me and say, hey, could you look at this? And I did it in my work. And then I'll go and I'll say, yes, you did. And then I can give you the mark, right? It's really just insurance. Okay, so it's not something that you have to worry about if you feel comfortable with what you submitted, and that's good, right? I'm not going to mark your written work because it is so it's going to be so different for everyone how you do it. So I don't want to do that. But submit any written work to the Dropbox on Moodle within 10 minutes. Oh, I had to make my highlighter so small earlier because I was all zoomed in there. Within 10 minutes of submitting your test, in case you need me to look at anything. Right? To fix marks. To fix your marks. Right? It's kind of just insurance. Okay. And yeah, so I apologize because I forgot that I didn't get you to do that for test 1 because it was all multiple choice, so there's no point, right? And so this is the first time that we're doing this in this class, although you guys know what to do. So if you need help uploading your work, then let me know in advance. So you only get the one submission, right? So you can go back and you can change your answer, but once you've submitted, you just get that one submission, right? So you can kind of lock it in and say, there. And then you'll have 10 minutes to submit your written work. And unlike the assignments, it's not going to tell you if it's right or wrong. Oh, I know, brutal. Right. I know, that's a test and that's a moray. So make sure that you have kind of practiced the assignments. So the assignments will be good practice for the test. Okay. So just kind of get comfortable with those types of questions, and then that's what you're going to see. Okay. Any other questions? It's going to be fine. Cool emoji, the sunglass emoji. That's what I want to see. Oh yeah, so chapter 6. So that's what I was confessing earlier, was I want to make you do a k-nearest neighbor calculation to show you how it works. So and I'm like this close to getting the code to work, so I'll post it after class. It's going to be a really small assignment. So the test will focus on chapter 4 and chapter 5, which are kind of the meat and potatoes of this whole, well, everything, right? Regression and classification, those are kind of the most important things. And then I'll post a small assignment, and I see the cool emoji now. Yeah, you got it. Here's the code. So there, I'll post a chapter 6 assignment, but I think it's only going to be 5 questions. So it's going to be really small. Okay, and but definitely try it before you do the test. Okay? Oh yeah, so an assignment, and I'll say it's very short for chapter 6. Yeah, which is on the test. So an assignment which is very short for chapter 6 will be posted after class today. Basically, as soon as I figure out this little glitch that I've got, then I'll post it. Okay, and it will be included on the test. Right, so focus on chapter 4 and 5, of course, and then a little bit of chapter 6. Okay, all we do is talk about tests, right? I think I'm so hopeful that we're going to have time to finish this whole textbook this next week, chapter 7. We won't be able to go into too much detail, and that's okay, but it might be nice to have seen all of it, and then you'll be more comfortable with it. That's what I'm hoping for. And then we've got our final exam, April 28th, evening exam. But for now, let's just focus on test 2. What I want to do is I want to have the option of doing a review day closer to the final, right? Because we're not going to do a review now in the term, so I'm open to hosting a review slot, which might be drop-in. I don't really have anything prepared, obviously, but we'll talk more about that later. All right. What did we say? What did we work on last day? Oh yeah, well, first, any questions about this test that we have coming up specifically, or maybe even the final, I don't know, before we start? Nope. All right, let's hop to. So we almost finished chapter 6, or there is more in chapter 6, right? There is more on boosting. However, I want us to focus on bagging and the random forest, because we need to be able to do those properly before we go to boosting. Okay, it's going to be a little bit more picky and just kind of finicky with all the hyperparameters that we need to set. And so it's not just, you let the defaults run. You need to be a little bit more kind of doing more fine tuning with boosting. So that's why I'm saying, no, that's not for us, right? With this little time that we have, we can't do boosting, but we can talk a fair bit about bagging and the random forest. So just for a little bit of review, we talked about decision trees, or kind of just tree classification models, right? So we talked about tree classification models. They look like kind of upside down trees, right? They start at the root, which is at the top, and then they flow down. They look like family trees, that type of deal, right? And so, and what's nice about these tree classification models is it goes through and sorts the data. It doesn't sort it, but it kind of classifies the data by similar groups. Okay, and so that similarity was measured by impurity, right? And so we talked about impurity, but we have a pretty good understanding just intuitively about what impurity means, right? How many were correctly classified versus incorrectly classified in each in each division. Okay, and so we've got this kind of top node here, and we have some rule, right? So if let's say if we're talking about maybe that loan data, I can't remember what the variables are, right? But let's say the easiest way to split our group is by if the person is a homeowner or not, right? Let's just keep it nice and simple. And so homeowner, oops, if it's 1, then you're in this group, right? If it's 0, you're in this group. Okay. And then from here, right, we might talk about age, maybe it's greater than 50. I can split that in 2, right? Because it's either yes or no. So either it's a 1, oops, keeps jumping around. I don't know why. I must be hitting it. 1 or 0, right? And then I might have a group here, or maybe I keep branching, right? And so it divides our data. And what it makes me think of is, so I was kind of a weird kid. I love organizing. And so often I would just take everything in my room and just everything like off the shelves, everything just kind of everything. I would pile it in the middle, and then I would go through and I would reorganize it, right? And that's basically what this tree classification is doing, right? I would put, let's say, all my Polly Pockets over here, right? All my Barbie things are over here, right? And all my books go over here, right? So you're kind of dividing the data by these clear classifications. And then as we get more and more detailed, right, I can specify very specifically, right? Maybe I have different types of books, right? So then I can divide them up into different types and stuff like that, right? So that's what this tree classification is doing. So our minds are really good. Yeah, I think so. Yeah, I'm like, I love organizing. So I'm like, okay. Yeah. So our minds are really good at understanding this, and that's a really good thing to be able to show to someone who doesn't know anything about the data, right? Doesn't care about the data. All they want are answers, right? Who's going to sign up for this subscription, for example? Who is going to click on an ad? Who's going to buy something from our store? Right, those types of things. That's all they care about, right? There's a lot of data that's running in the background. And if we have a tree like this, then we can easily communicate, okay, we were able to correctly classify this many people, so this is a pretty good stream or kind of branch of people to pursue, right? And so here, right, it might go down and maybe it's like that or something like that. It can keep going, and it grows, and it becomes more specific as the tree grows. So sometimes we say no more, right? We're gonna lob it off here. This got too specific. Then we can prune it, right? We can prune it back, and we can limit the number of nodes that we have, right? And that's something we can do in R as well, right? We can set the number of max nodes, right? And I think we can set the number of the depth of the branches. I can't remember. The textbook outlines it. I don't remember. Right. And so, right. So here we can limit the number of nodes. I think it's, sorry, let me just, I can't remember what it was called. Max nodes and node size. Okay. Yeah. I think that's what it was. Eek. Yeah. So we can limit the number of nodes in R. Well, if we were doing it by hand as well, right? And so this would be a very difficult thing to do by hand, especially if you have even just 1,000 data points. That's a huge set to be scrolling through. Maybe you have 20 variables and you're trying to classify a person as buying something from your store, right? So then you would look at, okay, who buys stuff from my store? And then you would look at some of those key characteristics, right? Those key demographics of who buys things at your store. And then that's who you target, right? And so that's like a by hand way of doing it. But of course, we can just do it in R or in Python or whatever you prefer. So we can limit the number of nodes so that our branches aren't too data specific, right? Because we're building these things based off of data, right? So we don't want to overfit the model. We can still overfit the model by training it to be exactly divvying up our data, right? That doesn't transfer well when we go to a new data set, right? And so we don't want to overfit it so that we have these very, very specific branches, right? And so so then we trim it back and we have these kind of general branches before it gets too overgrown, I guess. So we can limit the number of nodes so that our branches are not specific to the data that we use to build the tree, are not specific to the data we used to build the tree. Okay, which would be overfitting. We're used to overfitting in terms of regression, right? Where overfitting means including too many predictor variables, and it does really well because you have all these predictor variables, but it does really well with our current data, maybe not as well when we apply it to new data, right? So so that's something to keep in mind, right? You don't want to train it just to your data set and then it performs really well on your data set, but then when you go and apply it to another data set, it doesn't work so well. Okay. So a tree model has this this beautifully kind of mapped out sort of decision tree. I think a decision tree is something slightly different, but I mean similar. But it has this beautiful visual way that we can show people what our classification model is doing. Right? So a tree model, oops. a tree model is a useful visualization of our classification model, right? So a tree model is a useful visualization of a classification model, right? Of a classification model. Right? Especially if we need to explain it to people who are unfamiliar with the data or even data analysis, right? So a tree model is a useful visualization of a classification model that we can use if explaining a model to people who are unfamiliar with the data. A huge part of data analysis, right, is just getting used to the data, figuring out what are those variables, what are some of the key things that you're finding, right? Just kind of data snooping, I guess. That's bad, right? You don't want to look for things, but for significant interactions and stuff like that, for example. But you do want to know what's going on, right? What do I expect to see here? So who are unfamiliar with the data or even data analysis. So that's really nice. That's a huge benefit. But we know that we don't just want to have one model, right? We've talked about ensembles. I can never say, I always want to say it French, ensemble, but, and it is together, right? And so we put multiple models together, right? And so as soon as we do that, we don't just have one tree model, so then it becomes a little bit harder to visualize for sure, but we get typically better classifications out of it. So that's why we do multiple tree models. I'll say that's the end of our review. We kind of went a little bit further, I think, but that's okay. Okay, so to improve our classification, we often need to consider multiple models, right? So not just one tree, but multiple trees, for example. So to improve our classifications, we often need to consider multiple models, right? Or an ensemble of models. Okay. When we do that, though, we lose that beautiful simplicity of a single tree. Okay. So, however, when we consider more than one tree, it becomes harder slash, I would almost say impossible to visualize it like a single tree was, right? And so when we consider more than one tree, it becomes hard slash impossible, depending on how many you consider, to visualize the classification rules, right? So those are rules that we're going through to visualize the tree. Okay. So the reason we consider more models is to improve our classification. Now, here's where I would say, look at one tree, see how well it performs. How do we measure performance? We measure performance by impurity, right? And there's the Gini impurity and the entropy impurity, I want to say, which we didn't really talk about because the Gini impurity seems to be the most common one. But then we can look at the impurity, and that's how we would gauge how well our classifications are doing, right? So then if I look at multiple models and I don't get a lot better impurity or purity, I guess, then maybe it's better to just go with one simple tree model that you can easily present and talk about, right? It's just my take, okay? So simpler is usually better, but usually it improves our classifications if we consider multiple models. All right. All right. That brings us to bagging, which is short for bootstrap aggregating. And so bagging is kind of a fun word. Aggregating means put together, right? And then bootstrap means that we're resampling. Okay, and so those are clues, right, for what this method is going to do. Okay, and so the difference. So we are going to do an ensemble method. Okay, but what we're going to do is, instead of applying different models, so slightly different models to the same data, what we're going to do is we can fit the same model and we can apply it to bootstrap resamples of the data. So we get slightly different samples pulled from our big sample, right? Terminology gets confusing here. So we have our large sample, and I take a bootstrap. So every time I resample a portion of that data, right? And I think, did I specify? It doesn't, I didn't write down if it was with replacement or not. I feel like bootstrapping is with replacement, but I can't remember. That's okay. So, so bagging is an ensemble method, which really just means considers multiple models, right? Considers multiple models instead of just one. But each new model is fit to a bootstrap resample from the data. But each new model is fit to a bootstrap resample. Then what can we do? We're always going to have some outcome that we're interested in, whether it's numerical or categorical, so a classification, right? We're going to be able to take some average outcome, right? And so the bagged estimate, is the average, typically. So it doesn't have to be the average, right? But typically it is. So the bagged estimate, that's what we're calling this, the average of the models. So if you're doing a classification, then the majority of kind of overlapping classification rules, right? That's what wins. Yeah. Kind of easier to think about numerical data, because then you can just talk about, oh yeah, the average price that I got from running all these models was this, right? And so that's my prediction. Okay. So that's bagging. There's not much more to it. It's just a different way of collecting multiple models, so more than one model, and then we average those outcomes, and that's bagging. But the key is that you're fitting it to a bootstrap resample. So a portion of the data, but constantly a different sample, right, for each model. So here, each model is built using a slightly different data set. Is built using a slightly different data set. That's important, right? Because then if we have these slightly different data sets, and they all come from our sample, so they're not, they're not made up, they exist, and we know what those outcomes are, and we can test it, and we can do all these things. But if I'm taking little chunks, then I'm not overfitting to any one data set, right? I'm going to apply it to all these little data sets that combine to make up the entire data set, potentially, right? Not necessarily, right? There might be some who are left out, but in general, right, we feel pretty confident that they're all being included at some point in some model. And so, so that's a nice way to avoid overfitting as well, right? So that's good. Okay, so kind of one step up from bagging is the random forest. Now, the random forest is interesting because it's bagging. So it is still taking that bootstrap. We're leveraging that, okay, each model is built on a slightly different data set, right? But it has that added complexity of not only taking different data sets, right? So bootstraps of the data, but also it only uses a subset of the possible predictors. What? And it's not always the same subset. So it randomly selects some number of predictors. So if we have 20 predictors, then it might use 10 of them in a model, right? So it randomly selects the predictors as well. And that's pretty cool, right? And then once we put them all together, put all those models together, then we're going to have something that takes into account all the data and all the predictors, right? But individually, right, we focus on just a subset of the predictors and a subset of the data. So the random forest is kind of an interesting one. So it's a forest, so usually it's for trees, and a lot of these are for trees, although you could use them for other models as well, but usually it's trees. So it's a bagging decision tree, right? Which means that we're taking bootstrap samples of the data. So uses bootstrap samples of the data, right? to build multiple models, but I'll leave it at that. So it's a bagging decision tree. And how did I say it? And it randomly samples the predictors to consider for each model. Right? So it randomly samples the predictors to consider for each model. That's kind of cool and crazy. For me, it's like, wow, crazy. So how many of these predictors? So if we have P predictors, then as a rule of thumb, it would consider about the square root of P, right? And that's just, it's just a rule of thumb. So here, randomly samples the predictors as a rule of thumb. Sample the square root of P of P predictors. So that's just, so what does that mean? If I have 20 predictors, if I take the square root of 20, I get 4.47-ish. So then I would have 4 or 5 predictors, right? So for, not that is, e.g., for example, if P equals 20, randomly sample, oops, about 4 or 5 predictors for each model. So now you can see that you've got, or you can imagine, I guess, that you've got these many trees, right? So it is a decision tree, but each tree is built off of slightly different data. And now it's also built off of a different subset of predictors. So then our estimate is still going to be the average of those outcomes, right? And but I didn't write that down. But I think it's the bagged estimate again, which is the average of the outcomes. So I'm not going to commit to that, and I can't remember, but it's okay. I can't remember where to find it either. Oh well. I'm pretty sure it's the average estimate. The random forest estimate is the average of the models. And I'm going to be clear here. I need to confirm this, but I'm pretty confident. Need to confirm this, but I don't want to flip through and read that whole section again right now. So I'll confirm it, but I'm pretty sure. Okay. Okay. And it'll say. Okay. Good. So that's the random forest. So it's a little bit more more advanced, right? We worked from kind of the simplest, from K nearest neighbors, and then we talked about decision, so trees, And then we talked about bagging, which is just collecting multiple trees. And then we moved into the random forest, which is a little bit more advanced, right? Because now we're not just randomly sampling the data, we're also randomly sampling predictors. What's really neat about the random forest is that it has this ability of picking up important predictors. So then it'll start to include those predictors, and it can even do things like, oh, I think there's an interaction here that I'm going to consider, right? And then it starts incorporating even interaction effects, and that's really cool. So it's kind of this interesting animal, right? That kind of, oh yeah, these predictors seem to be important, so I'm going to focus on these guys. And then, oh, there seems to be an interaction here, so I'm going to include those as interactions. And then I'm assuming what it does is if it tries it and it doesn't yield an important result, right? So if it doesn't yield a significant result, then it would say, nah, I'm not going to try that again. And then it would just keep going and keep focusing on those important predictors. So the random forest algorithm has the ability to automatically determine which predictors are important. That's pretty cool, right? And can even detect interaction effects, right? And include those in the model, and can even detect interactions and include them in the models. Right? We're not going to want to see what this algorithm looks like. It sounds pretty crazy, right? And we can, right? But let's just let R or Python handle that heavy lifting for us. And then just keep in mind that, okay, how does it work? Well, it takes a random sample of our data, and then it takes a random sample of predictors, and it starts to kind of pick up on important predictors as it goes, and then it includes those in the models. And then we put all those models together. So for all of these, right, how it picks up on important predictors, for example, right, and a lot of other things. How big should the tree grow? How specific should the tree be? Right? How we adjust those are called hyperparameters, right? So they're those little arguments that you add in your R code, for example, or in Python, right? Where you tell it, okay, I want to have kind of the most basic version that we have. If you make a histogram, you can adjust the number of bins, right? There's some default number of bins, right? So there's some argument there, but you can adjust it and you can force it to be something else, right? And so a lot of the defaults are fine, right? Especially for these models that we've talked about, right? But you might need to adjust them. So we may need to adjust the hyperparameters which are really just kind of arguments in our R code. I say R, but of course I mean R or Python or SAS or S. Did you guys know that? So S was this programming language, and that's what R is based off of, but S you had to pay for. So then they built R, which is free, and it works the same way. So anyways, so if you look up S, it's obviously not used anymore because there's R and it's free. But one thing to keep in mind is that there are some firms who can't use free software because there's no guarantees, right? So then you would have to use S, for example, right? Or SAS, or all these, I'm pretty sure R is based on S. But S is just the paid version, but it's not as maintained as R is at this point. Anyways, I might be wrong. I don't know, but I'm pretty sure. Yeah, maybe you wish it was based off of a different language. But once you know R, then you know how all of them work pretty well. Okay, so you may need to adjust these hyperparameters to improve your classifications, right? Or to improve your estimates. So when I say estimates, I mean your numerical predictions or your categorical classifications in general. I'll call them estimates. Okay, so we may need to adjust the hyperparameters to improve our estimates. Okay. And maybe what I'll say is beyond what the default settings can give us. Beyond what the default settings can give us. So for example, a hyperparameter would be things like max nodes, and what was it? I had it out, some of those hyperparameters. Sorry, let me go there in my mind, not my mind, node size. So for example, node size and max nodes, right? And those would be arguments when you run your random forest, for example, or maybe your tree, right? And so these are what we call hyperparameters, and you might need to tweak them, right? So there's some default, of course, I just let the page go. I think the default node size is 5 in R, and anyways, okay, I'm not, I say I don't want to do it and then I do it. I had it, I can't find it. So these are going to have some default settings, but you might need to tweak them, right? And you've probably seen that before, right? Where maybe your graph has some default axes, right? But you need to tweak them. And so those would be considered hyperparameters, right? But in this case, they're specific to the model, right? Because we're kind of twisting these little knobs and making adjustments to our models, right? And how they work. Okay. And so what's nice about bagging in general and the random forest is that you don't need to make too many adjustments to these hyperparameters. You can still get pretty good estimates without changing too much. So we may need to adjust the hyperparameters to improve our estimates beyond what the default settings can give us. Adjusting the hyperparameters can also help us prevent overfitting, right? So things like the node size, right? That controls, or I think, let's talk about the max nodes, because I can't quite remember what the node size does exactly, but the max nodes, I think it's the smallest node that I can have before splitting it again, right? I don't want to split it past this size, but don't quote me on that. Whereas the max nodes, that's obvious, right? It's the max number of nodes that I want in my tree. I don't want to have a tree with 100 nodes, because even if I am able to talk to my client about it, I don't want to do that, right? Oh, and then if this happens and this happens, if this happens and this happens, or if this happens and this happens, and then you get very, very specific. I don't want that, right? So then I'm overfitting to the data most likely too, right? So adjusting the hyperparameters also helps prevent overfitting. So what's really nice is that bagging slash the random forest. Remember, the random forest is just bagging with that added little bit of extra, because it also only uses a subset of the predictors, right? But otherwise they're the same. So bagging and the random forest, those can be done with relatively few adjustments to these hyperparameters. So you don't need to be really kind of in there and nitty gritty and know about all these hyperparameters that you need to make adjustments. It's like tuning a music instrument, right? You're kind of making these adjustments. And so what's nice about bagging and the random forest is you don't really need to make a huge amount of adjustments. So bagging and the random forest, I'll make a little bullet here maybe, can be done with a relatively few adjustments to the hyperparameters. With relatively, and in my notes I use the word tuning, so I'm actually going to use that because it makes me think of tuning like a music instrument, and that is what you're doing, right? Your model is your instrument, right? And you're just fine tuning it, right? And so bagging slash the random forest can be done with relatively little tuning, right? We're tuning. Tuning just refers to adjusting the hyperparameters. Okay. Now, we don't know what boosting is yet, but I will tell you this, is that boosting is going to require a lot of those adjustments, which means you have to know what they all do, right? You have to know what your goal is, and that's a lot, right? That's what makes the boosting a little bit harder, something that we should probably put off and not do until we're very comfortable with bagging and the random forest and the k-nearest neighbors, right, before we get into boosting. So that's why even at the beginning of this chapter, I said, okay, let's focus on these few. And then there's boosting, and there's lots of different ways that we could boost, but we're not going to get into it. Okay. And so boosting. Boosting requires a lot of tuning. Okay. Okay. So for this reason, boosting is a lot more complicated, and we're not gonna do it until we're comfortable with bagging in the random forest. So for this reason, boosting can be a lot more complicated and we don't really want to do it until we're very comfortable with the other methods that we have, right? So for this reason, more complicated, and we shouldn't attempt it, right? And I mean attempt, you can try it, right, for practice to see. That's the only way that you're going to get comfortable with it. What I mean is, if you're working with a client and you're not comfortable bagging, then don't try boosting, right? Because fitting those hyperparameters, you could find very incorrect results, right, if you didn't set those properly, right? Oh, and I think the textbook had a cute example. It's like, so bagging and the random forest are like any normal car, like I don't know, a Honda Civic or something, whereas boosting is like driving a Formula One car, right? I don't know. So it's kind of like this fancy piece of machinery, but unless you're comfortable getting in there and driving it, don't do it. And it's okay, right? So, and we shouldn't attempt it until we are comfortable bagging and I guess with bagging, I should say. With bagging and the random forest. Yeah. Okay, so there are many different types of boosting, and the textbook goes through, and there's all these kind of, some of them are trademarked, right, because it's such a relatively new field, but there are many different types of boosting, okay? But in general, what is it? Oh, since I'm on a new page, I'll just jot down here, just as a side note, there are many different types of boosting. And I'll say, see the textbook for some examples. See the textbook for some examples. But in general, what does it do? I guess I should write that down. But in general, boosting fits a series of models, and usually they're trees. You can do it with other things, right? You can do it with a regression, but you can probably do it with k nearest neighbors, although it's kind of simple. But what happens is, but in general, boosting, it fits these models, and what it does is it doesn't just blindly fit the models, right? What it also does is it tries to minimize the error of the previous models, right? And so what it does is one of the versions is it puts a higher weight on observations that were misclassified, for example, right? And so that's interesting. It says, oh, okay, I didn't really capture these guys, right? So I'm gonna weight them a little bit more, or potentially downweight the ones that I correctly classified because it was easy for me to pick up on those. right? And then so I put a higher weight on those ones that I missed, right? And then it tries to reduce that error by doing that, right? So it fits these successive models, so many, many, many models, right? And then it's constantly trying to minimize the error. Okay? What's kind of disappointing is that's very fancy stuff, right? But the results compared to a random forest, for example, are about the same-ish, right? There are scenarios where, of course, it's not, but the textbook example even shows that it's not that different. Okay, so that's why I say it until you're comfortable, right? So there are many different types of boosting, but in general, boosting fits a series of models and I'm going to say usually trees, but each successive model tries to minimize the error of the previous model. Usually, and this is a really long run-on sentence, but I think I can probably throw a period in here somewhere. There are many different types of boosting. See, no, I'm going to stick with the long run-on sentence. And so I'm going to finish it off with, so it tries to minimize the error of the previous model, usually. So notice how I'm saying usually. So there are these different types, and of course, but usually by applying weights to the misclassified data. There, that's the end of my sentence. Okay, so there are different methods that we can use, but in general, right, it goes through and it fits a model, and then it figures out, okay, who did I misclassify? And then it weights those probably higher, right? Or you can downweight the ones that you got correct, right? So they're not playing as big of a role in your model, right? But we're still including them. And then we're trying to focus on those ones that we misclassified to ultimately get our final model closer to correctly classifying as many as we can, right? Okay. That's all I wanted to say today. I think that's good for chapter 6. Yeah. Test 2, Thursday. No class. I should. So of course, just as before, right? Test 2. So we have no meeting on Thursday, right? You can use the class time to do the test if you want to. Got a little smush there. Should have wrote it here. Oh well. Okay. If you have any questions, let me know. Otherwise, good luck on the test. And we'll post another lab for Friday. Remember, I did adjust the due dates. Let me see here. Chapters 4, 5, and 6. Nice. I'll try my best to keep it easy. Oh yeah, I adjusted the classification lab due dates and the assignment due dates, so they're not due until, I want to say, tomorrow or Thursday, just to give you a little bit of time. All right, I think that's good. If you have any questions, let me know, but I'll stop this recording and good luck on your test.